Swayam Prabha. Digital India. Educated India.
Welcome to 34th lecture in Mechanics of Materials. We started off looking at some basic concepts in mechanics, and then we looked at 4 equations that connected those 4 concepts, and then we went ahead to solve some boundary value problems using those concepts and equations. From there we estimated what the displacement and the stresses in the body are, and then we used the failure criteria, which was a material failure, so to speak, wherein we said that if the stress exceeds a particular limit, then the failure of the body would occur. In the last 3 lectures, we are looking at various failure criteria for pressure, hydrostatic pressure sensitive and hydrostatic pressure insensitive materials. In particular, we looked at Tresca criteria and von Mises criteria for hydrostatic pressure insensitive materials, and then we looked at Rankine or maximum normal stress criteria, Moore-Coulomb criteria and Draga-Praga criteria in quick for pressure sensitive materials. Okay, and then we said that if the stress exceeds a particular limit defined by the failure surface of these failure theories, then it will fail, or it is on the verge of failure if it is on the failure surface. That is one mode of failure. There is another mode of failure wherein a given body would fail just because of stability reasons, meaning if you have a ball which is sitting on a trough like this, okay, if I move this ball a little bit on either side of the trough, it will return back to its equilibrium position. Okay, on the other hand, if I have a ball placed on a surface like this, if I move this ball on either side, it goes to a totally different state of equilibrium state. Okay, so basically what happens here is a small disturbance alters the equilibrium state of the body. Okay, similarly I can have a situation wherein I have the ball somewhere here, small disturbance will take it to somewhere here and will stay put there. There won't be further deformation. Whereas the second case, a small disturbance would take it to some position here. Will take it to some position here or much more deeper, depending upon how the shape of the surface is. Here, if I disturb it, it will come back to its original position. Here, if I disturb this, disturb it somewhere here, it will return back to its original position. Okay, so you want the body to be in this state, which is called as the stable equilibrium state. You don't want the body to be in this state, which is called as unstable equilibrium. Or neutral equilibrium is okay, but you still don't want because it produces large deformations. This is called as neutral equilibrium state. To understand this in terms of a structure, think of a funnel placed on its base. There is an equilibrium configuration of the funnel. Okay, flat edge funnel based on its base. Okay, now what happens if I give a small disturbance? If I tap this funnel to occupy some position like this, some position like that, then it will restore back to its original state. It will come back to its original state because there is a corresponding moment which will help it come back to its original state. Okay. On the other hand, if I have a funnel based on a strip like this, okay, a funnel based on a strip like this, then if I turn it, the CG of the funnel falls outside the base of the funnel. If I tip it somewhat like this, okay, the CG falls outside its base and then it will topple over. Okay. On the other hand, for neutral equilibrium, I can have a funnel resting on its sides. Funnel resting on its side. This is an example of a neutral equilibrium configuration, wherein if I perturb it, it will stay put in the perturbed position. Okay. So basically now you want the body to be in a stable equilibrium configuration because that is a state which you prefer the body to be in. Okay. So that it doesn't show large deformations or it doesn't see large stresses in the process of going to unstable equilibrium states. Okay. Now next thing you have to understand is, till now we have been writing our equilibrium equations in the undeformed shape. Okay. For example, if I take a beam element, if I take a beam which is simply supported and we idealize it as a line element like this, wherein it was the axis of the beam, and you add some loading coming in here, you know that the beam will deform into some shape like this. Okay. If it deforms into some shape like that, then you didn't account for the fact that you didn't write the equilibrium equations, the deformed configuration. That is, you didn't say whether this force remains vertical or perpendicular to the deformed surface. Okay. If it remains vertical, then whatever we did was somewhat appropriate, but if it remains perpendicular to the deformed surface, then the lever arm should change. Okay. Those effects we didn't consider, we just took that the load to be acting on the undeformed shape, and we wrote the equilibrium equations to get dmx mz by dx plus by equal to 0 and so on. The equilibrium equation that we got were based on undeformed configuration equilibrium. This is evident when you look at a truss analysis which you would have done in your previous course in engineering mechanics. So when I have a triangular truss like this, which is simply supported at these ends, and I add some loading coming in here P and Q, you didn't ask the question what is the deformed shape before writing the equilibrium equations. You wrote the equilibrium equation in this undeformed shape and you assume that the deformed shape will be close to the undeformed shape, that it won't matter significantly. Okay. That's a good enough argument if the deformations are small, but what happens is these tell you that there is only one deformation that is possible for a given truss, since you are writing the equilibrium equation in the undeformed shape. Okay. If the truss were to deform, then you will find that there will be multiple equilibrium states that arises which are possible. To illustrate that, let us look at an example wherein I have this 2 element truss with a point load P acting vertically down. Now if I assume that this is not a small deformation problem but a large deformation problem, then I have to account for the fact that this stress will deform into some shape like this, wherein this deformation delta y is significant. Okay. Then what happens, you will see that there are more than one solution that becomes possible. I am going to illustrate this in this lecture by not using this complicated truss which is simple but yet complicated for our purposes, but I will demonstrate it with respect to a single member in compression. Okay. For example, when you think of a member in compression, say a column which is subjected to a compressive force P, we will think that it is going to deform. This is like a uniaxial state of stress, and hence we will think that it will deform into some shape like this, right? This will happen if the column is what is called as a short column or a stout column. But if the column is slender like a scale, then you will find that this is not what happens, but something different happens. Let us see what happens. I have the scale which is slender here in this dimensions. Okay, I am applying a compressive stress. You can see that it deforms quite significantly in the lateral direction. It is not getting compressed, it is not going down like this. If I apply a compressive force here, you can see that it is bending on either direction. Okay, it bends on either direction, but it doesn't bend in this way. It doesn't bend in this way, but it bends only in this direction or in this direction, depending upon some criteria. Okay, it bends like this or it bends like this. Okay, it doesn't do what we saw as it would do if it were a stout or a short column. Okay, so basically now you find that there is a discord between your analysis expectation and the way the body deforms. So you have to reconcile this. The reconciliation is by what you are going to do in this lecture. Okay, the reconciliation arises because you wrote the equilibrium equation for this column in the undeformed shape, whereas you have to write it in the deformed shape. Okay, so now what we will do is we will take this column instead of a cantilever fixed and a free end column. We will look at a simply supported column. The pin here and a roller here. You understand that a roller should be in this direction because only then will allow for axial compression. Otherwise, the member won't deform. Whatever load you apply, this support reaction at B will take all the axial load that is applied. Okay, if you are a hinge or if you are a roller in the other direction, the support reaction B will take all the reaction force and not allow the column to compress. Okay, now let's assume a coordinate system. Let's still assume this is X. This is Y, and outside the plane is Z. Out of plane axis is Z. Okay, so let's assume the cross section has some cross section shape which is arbitrary, which is Y and Z, acting like that. Okay, now you would expect that this column to deform into some shape like this. Wherein the roller moves down here and it becomes a roller there. Okay, due to the applied load. But let's investigate whether there is an alternate deformation possible, which is this. Okay, that is the column to bend, like what the scale did in our case. Okay, can bend along Y direction or can bend along Z direction. What is the criteria? You will find out in a short while. Okay, in which direction it bends. Okay.